Welcome to the lesson on tornado track analysis, the center line using the Damage Assessment Tool. I'm Jim Ledoux and I will guide you through this lesson. The objectives are all about analyzing the track center line. At the end of this lesson, you'll understand the characteristics of the track center line, recall tips for identifying where to begin and end the track center line, interpret the track center line with appropriately labeled point data from ground surveyors, and conceptually adjust the track center line with the satellite and aerial imagery. You'll also recall the best practices for analyzing the track center line, identify the diverse treefall configurations marking the track center line, and identify the situations where the diversity of tornado behavior may complicate the analysis of the center line. Most tornadoes exhibit a confluent damage pattern. As explained in the lesson on field data collection, the center line is where the damage direction exhibits confluent patterns. Often this is easiest to see in a pattern of tree fall that you can see, for example, from this tree damage, where trees to the left fell to the right, while on the right they fell to the left. There's more nuance to confluent tree fall patterns that I'll explain later in this lesson. The center line also happens to be where small debris accumulates. The picture here shows an enhanced area of accumulation from a significant tornado. When identified from the ground, the surveyors should indicate center line. But perhaps sometimes other names may appear, such as confluence zone. But if a surveyor is absent, look for these accumulation zones in high-resolution aerial or satellite imagery. The big question is where to start and end the center line. Since we are using the center line to identify tornado path, let's start at where the evidence shows the tornado began, and likewise where it ended. This means I should bring back an old but still valid reference from Fujita where he identified tornado tracks as simply narrow and more intense damage. For most events, the onset of a tornado track is quite clear, as damaging winds only occur within the bounds of an intensifying ground-based vortex, as in point A in these various track configurations. Likewise, on the other end, the narrow damage track terminates with no surrounding damage, as the points labeled B indicate. As this example shows from Lady Lake, the tornado track is long and narrow, with an obvious zone of more intense damage denoted by the loss of green vegetation. It certainly was plausible considering the radar data and the initial guess of the damage track. And the damage directions were non-divergent. On the other hand, more intense supercells with widespread damaging mesocyclonic and rear flank downdraft winds, or mesovortices embedded in damaging QLCSs, means that the tornado track may evolve out of otherwise damaging downburst or straight line winds. In these cases, the tornado track should still be more intense than the outlying damage, and perhaps more importantly, non-divergent. Thus, the start and end points for a center line should be where the damage is non-divergent and more intense than anything that you have surrounding it. At this point, I'll take you through an 8-minute walk. This is a walkthrough in the DAT to produce a center line. The objective of this outline is to show you a sequence of steps for analyzing the center line of a tornado damage track using ground survey points and high-resolution satellite data. Now, other tornado events may dictate changes in the configuration of the analysis and even with this demonstration. I don't walk through an analysis of the entire track, but instead I walk through sections of the track that satisfy the main objectives of this lesson. Okay, let's go ahead and start by drawing a center line here, and we'll start with the points along the tornado track that indicate center line in them. But first, we'll go ahead and add a path, and we'll draw this general broad brush center line from start to beginning by adding path and adding a few waypoints along from the starting point where I have points of this tornado track to the ending point, which I assume is the end of the tornado track. We'll add an event ID. This event ID will be the same right to the letter as everything else that we have. And we'll go ahead and put in the start date of the tornado track and the start time, which I'm going to make 2350 UTC. The end date, well, this tornado went across the UTC, 0Z UTC, so we'll go to December 27th and put in 00 and 10 UTC, I believe, or 5 UTC. Well, I put in the maximum EF rating of the tornado for this and a wind speed estimate, a maximum wind speed estimate. I can put in a comment here saying track center line and then add the path. We'll say no to quality control and we have the path added. Now I'm going to go ahead and zoom in and adjust the center line to appropriately labeled points that were done so by the ground surveyors. Hopefully the ground surveyors added center line where they thought they saw confluence and damage. So we'll start off with this neighborhood here that we used in an earlier lesson to show you how points are added. And we'll go ahead and click to choose a feature, for example. Maybe this house that has EF3 damage might be the center line. But the surveyors didn't put any comment in there saying center line. So let's go ahead and search a little bit more. Let's go to the west a little bit. We have an EF2 damage here. And sure enough, the surveyor put track center. I'm going to say that's center line. I think the surveyor meant that as well. So that's the place where I'm going to go ahead and adjust the center line. So let's click on the feature, the damage path, go in and edit path. And there's a vertex there nearby, and I just move it over. And then at this point, I'll go ahead and double click, hit no for quality control, and you see the path has been moved. At this point, I'm going to go ahead and now adjust the path center line, looking at tree fall and the confluence of tree fall using the world view satellite imagery. So I have to pick the appropriate time and time buffer. And right in there, I have the world view. I could look at true color, for example. True color gives me actually, literally what it says. It's the true color using 3 channels, red, green, and blue on the worldview satellite. If I zoom in here, what I want to see are individual trees, and that's my goal. Let's see if we can see that. Okay, this is a field here just south of our neighborhood. And you notice it's going to be difficult to see trees. I need higher resolution. The true color doesn't quite have the resolution that the panchromatic does. And at this point, I'll go ahead and zoom in a little bit more. And there we go. I'm close to seeing the individual trees, and now I can. The one challenge here is to discriminate individual trees from the shadows cast by the trees themselves. Sometimes it helps to look at the original imagery, the background, and then compare it with the world view. So I think I see damage confluence, tree falls falling in different directions to the northeast and to the northwest. And so this is where I'm going to go ahead and edit path and draw my path center line in between the trees where they fall and converge to each other. Okay, now we're going to go ahead and zoom out again and look at adjusting the center line, not due to the confluence of trees, but based on the debris and accumulation of debris and the direction of debris. So we'll go to a neighborhood further northeast that has a field. off to its southwest, and then another neighborhood. And we're zooming in, and I think already you can see that between the two neighborhoods, there's a kind of a line or a debris trace, and we're a little bit off on the center line that we just drew, kind of in a broad brush. So zoom in, get a closer look. You can see chunky large debris, and then this line that extends across the field here kind of wavers back and forth a little bit. And that line extends intense damage on the houses on both sides of the field. We zoom in and we can see debris extending to the north-northeast from one structure and to the east-northeast from another structure to the west, which indicates some kind of confluence going on. So we're going to go ahead and adjust the center line to match better with the debris accumulation zone there. So we'll add 2 waypoints and make a further refinement. Okay, so I think that matches up. You can see that it matches with the debris accumulation better, and the path has been moved. So at this point, if I was to continue moving the center line off to the northeast, I would do so. But you can see right now as I switch on and off, at least across the field, it looks like it matches up better. The walkthrough highlights a number of important points that I'll emphasize here. I started the path by drawing a center line roughly from start to end of the tornado track to just simply start the process. In the Identify and Edit toolbox, I make sure that I enter an event ID and that all points, paths, and polygons match the same event ID. For instance, I would suggest using year, month, and day, and then the town name, and then a 2-letter state ID, such as 2015 12/26 for December 26, Rowlett, Texas. That's the case that we used. And if there is no town nearby, then maybe there's some other geographical marker that makes this event unique. After that, I enter the starting and ending date time for the tornado track, enter the maximum EF rating for the tornado event, and I may enter casualty and damage figures if I happen to have them. Then the rough cut center line's going to need some adjustments. And this is where you drill down and match the center line to the field survey comments suggesting center line or some other similar comment. And then adjust the center line to the field survey start and end point comments. Then I adjust the center line to the satellite and aerial observations of confluent damage, fall, and direction, maybe debris accumulation paths. And then the center line, again, very important. It may or may not align with the most intense damage. There's more to the center line that may help alleviate any confusion about confluent damage direction patterns that you may see. To explain this, let me describe some fundamental geometry of a tornado vortex. Consider a tornado center with a radius of maximum winds denoted by the circle, and a motion to the right labeled v sub t. Tornadoes have 2 components of velocity, one that's radial, v sub r, and the other that's tangential, v sub theta. And these combine to produce a circular velocity, v circ. When you add the motion of the tornado to the circular velocity, you also get the total velocity, v, that's strongest on the side of the tornado following its motion, and weakest on the side opposing it. The angle alpha is the angle between the radial and total velocity on the side where it's maximized. This alpha is what we will describe as how it affects the appearance of the confluence zone coming up. The tree fall pattern research is relatively mature, and it's been used to produce tornado wind field maps for major tornadoes such as Joplin of 2011 and Tuscaloosa the same year by comparing modeled patterns to those observed. The modeled versions of tree fall patterns also visualize the confluent patterns that are often observed in the field and are capable of showing what kinds of patterns to expect based on tornado strength, motion, and the angle between the radial and actual velocities, or the alpha. So let's start with this example here. where perhaps the tornado is mostly inflow, and or in the extreme case, all inflow, where alpha equals 0. And in this case, if the tornado motion is, let's say, half of the circular velocity, or v circ, and the trees are weak compared to the tornado, then you get a somewhat non-intuitive but very plausible pattern where the trees fall opposing the motion of the tornado, where the motion of the tornado is up toward the top of the display. It's quite possible the trees fall that way before the arrival of the tornado center, and the confluence zone appears, however, and coincides with the center of the vortex. As the trees become stronger, or you could say the tornado weakens, the confluence zone appears to weaken, or appears to actually fall in the direction of tornado motion. But the confluence zone is still apparent, and it's aligned in the same location near the vortex center. A weaker tornado yet results in a narrow damage path, but the same confluence zone appears. Now let's go to alpha equals 30 degrees, or convergent rotation. In this case here, when the tornado is strong, we get a confluence zone where the trees fall, again, opposing the tornado motion. But more trees along the tornado periphery fall in line with the tornado motion, or towards the top. Then as the tornado weakens, a confluence zone still appears, but the individual trees begin to shift directions until eventually aligning with the tornado motion. Now, when alpha increases to 60 degrees, the confluence zone becomes kind of hard to detect. It's still there, but not so much with the strong tornado scenario, and maybe a little bit more so with the weaker ones. Perhaps you may have noticed that the confluence zone shifts around. The confluence zone doesn't change locations for the purely inflow tornado of various strengths. But with the convergent rotation tornado, notice how the confluence zone shifts to the right as the tornado strength weakens. And for the more rotational but less convergent zone, the shift to the right is even more pronounced. The shift in the center line means that it can be offset from the vortex center. This example from Lombardo and co-authors is a treefall simulation of a significantly strong tornado depicting a confluent one. It's also got a center line, and notice how it's displaced to the left of the vortex center itself. This displacement can shift the relative position of the confluence line to the vortex center, and so it's important not to try to guess where the vortex center is. Also, notice that the confluence line is likely left of the strongest winds, as you can see from the magnitude of the wind field here in this model. A good analysis of the center line follows the confluence of the damage direction or the accumulation of small debris, and it provides useful information for our users to be able to extract the properties of the tornado for future risk assessment. Now that you have the considerations of the confluence line in place, let's take a look at some examples. This one is a classic confluence line of fallen pine trees following the motion of a tornado as it moved from left to right across the scene. The center line would be drawn down the center of the confluence line, and in this case, it appears the center line is also co-located with the most intense damage. Let's take a look at another example, in this case, crops. This is from a paper of Sko and Kogel in 2016. And here the center line would be drawn along the confluence of bent stalks and grass, as this example shows here. Sometimes stalks from recently harvested crops may be pulled out of the ground and accumulate in channels, like the debris accumulation zone I showed earlier. Use these here to draw the center line. As I demonstrated in the video, a survey analysis of damage direction is really important in identifying the center line. So damage direction observations can reinforce the surveyor's comments, or if lacking, at least be a backup. Some tornado tracks may not exhibit a center line. Fast-moving, weak tornadoes may not show a center line since only the strongest right flank winds following the vortex center may cause damage. In such cases, draw the center line on the left side of the damage, as this image of crop damage shows, as well as a schematic posted long ago in a damage surveying publication in the early 1990s. Strong, slow-moving tornadoes will blow tree and structural debris well in advance of the tornado center, and that results in an arc of debris in the direction of the wind. If little is left over once the center arrives, a safe assumption that is, then it's likely that a confluence zone will be hard to detect. If none is detectable, then you go ahead and put the center line straight down the tornado track where the debris and tree fall is directed normal to the motion of the tornado. However, evidence of a confluence zone may exist as debris accumulation. That means that you might want to go ahead and draw the center line in such cases right along the confluent debris fall, and that would be in the absence of any confluent tree fall. Multi-vortex tornadoes may exhibit complex confluence lines, especially if the only regions of damaging winds reside within the subvortices. Ideally, you would want to analyze multiple confluence lines following each subvortex. Well, while this is possible to do in the DAT, it wouldn't be very practical to name each subvortex an event and then have to draw a total event path anyway. So instead, go ahead and draw the center line through the middle of the subvortex paths as they transverse across the larger tornado path, as this red contour shows. This concludes all the information that I have to present to you about drawing the center line. Let's go ahead and summarize what we've talked about. With all the considerations in mind, let's start off with one, and that is confluent tree fall patterns may include trees blown toward or away from tornado motion. They both count. But a confluence zone may or may not follow the vortex center or the zone of most intense damage. The drawing center lines when tornadoes lack confluence zones. Watch out for this when you have fast-moving or weak tornadoes. In this case here, you go ahead and draw the center line on the left side of the damage track. For slow-moving, strong tornadoes, the tree fall may not have a confluence zone. You could look for confluent debris patterns in open fields, or if none are found, then you could go ahead and draw the center line where tree fall crosses normal to the tornado motion. For multi-vortex swaths with multiple confluence zones, here you'll want to go ahead and draw the center line halfway across the subvortex track in the direction of tornado motion. Before I depart this lesson, I'd like to remind you about some quick guide modules that are available on the NASA Sports site. The one that you see here on the upper right is about satellite imagery and product interpretation. If you'd like to know what satellites are used, what the resolution is available for each of the image bands, go ahead and take a look at this module here. This concludes the lesson on finding the center line of the tornado. My contact information is listed here, and also for the author of the DAT tool. Have a good day.